Hey, welcome back to the channel. Good to see you again. Hope you're all well. Thanks for joining. So today on the bench, I have another item that I purchased with help of you guys. Whenever you guys donate money to me or the channel, I turn around and I reinvest it into items that I can bring on and do repairs on and hopefully learn something from, and you guys can learn from too. And you never know, might have some fun along the way, but who knows. So this is the way it arrived. It's got absolute minimal packing. This is only like not even 4 inches high, so I don't know. And it's quite heavy. I'll show you the bottom. Got it wore through in 4 spots here. So I have a feeling this thing might be in a little bit of shipping damage mode. So let's open this up. Not very much packaging on this whatsoever. See the minimalist packing the guy did. So yeah, I scour sometimes for items that need repair, and I bring them to the channel, and I won't just buy any old junk. You know me. Oh yeah, you do. But let's see how this one looks. What is holding her? Oh wow. It's a little better than what I thought, but look at this. That helped. Well, kind of. The fuse holder is a little broken. But let me get it out of the box. Alright, so there it is. It's out of the box. And actually survived not too bad. Even though it's a little... chassis is loose, these screws are loose. So it probably had... well, these screws are loose. These screws are loose, so it had a rough ride. But it's all... the front panel's intact and it's not damaged too bad. The rack pulls are scratched. And the ears, the rack ears are kind of dinged up. But you know what? That's probably seen rough service. And then we got the top that's really rough looking. Let's look at the underside. Looks pretty good. Now this is probably some gear amp from maybe a band, I don't know. I have no idea. It looks pretty rough shape for it's been used. Some scratches up here. It is heavy. It is heavy. And it's got the power cord. Everything looks good. This is your choice, the Carver model PM-350. So this was, I put the 3 amplifiers up for voting to see which one you guys wanted to see next. The HK Citation 19, this amp, and the Onkyo. And this one came above the rest. Now the race was tight for all 3. They were all over 30%. I think there was only a few percentage points between the bottom 2 and the top 2. So this is the clear winner. We're going to get to it. Don't worry, I'm going to do the other ones as well, so we're not going to miss out on anything. But I just wanted to get a little insight from my viewers as to which order to do them in, because you know, you guys have a say in what I do here too. So this is an eBay find. It's pretty beat up. As you can see, it's had a rough life. It's got some battle scars here. And wait till you see inside. It's not, you guys picked the hardest one for me to fix. So the top off, it's kind of dirty, grungy. It's just like everything else in this thing. Let's I have a bag of screws here because I was poking in here earlier. Okay, let's have a look at this. Okay, so I don't know, it's pretty dirty inside, but we have somebody gave up on this one, I think. Yeah, I don't know if they tried repairing it or not. We got some cooked zones here. Got resistors flopping in the wind. And I think the pads underneath are completely gone. We have a motor that feels like it's seized or not working. I think the brushes might be completely worn out. Not sure about that. We've got some more burnage down here underneath. I don't know if you can see, there's a resistor here that's burnt and naked. It's got no more skin left. And the one next to it just looks cooked too. So I'm not going to be power plugging this one in anytime soon. Underneath the front we got two big bulk filter caps, 9,000 microfarad at 100 volts. We got our massive transformer with a lot of iron. There's a lot of iron here, so expect to see some high power outputs. And then down here it looks like we have our triac control. Looks like it's because our triac is right here in the corner, and this looks all like triac control. So that's probably the voltage regulation for the power supply. Some more bulk filtering here. Another cooked resistor that's missing. And some wires that are just flopping in the wind. So we got a lot of damage here. Here's some more damage. And this is cooked. So yeah, we got a lot ahead of us here. So looks like it's got a 2/3 removable bottom. So let's take this off. There's a big scorch mark here. Wow, and the carnage continues. Look at all this. Somebody's been working on it. We got XX over here, some desoldered transistors, 2 of them. Scorched earth over here. And then we got lots of areas where the pads have totally lifted off the board. And so they probably took one look at this and said, oh, this is too far gone. We can't do anything for you. The amount of hours they need to put into this to, you know, do repairs around these board areas here. It's all doable stuff. It's all fixable, but it just takes time. And the people don't want to invest time. There's a resistor completely missing here. The pads are missing, the traces are missing, and all I see is fiberglass. This thing's in bad shape. But it's going to work when I'm done with it. I'm guaranteeing you that. So many cooked areas. This all needs to be reworked. Down here it needs to be reworked. Wow. Well, I was looking for a challenge and I found it, I think. So, yeah. What is this here? This burn mark is this component, which is, looks like a resistor. Yeah, fun. Let me just quickly check these strands. I bet you they're blown. If somebody's got them marked, they are definitely going to be gone. Let's try this. No, that's good junction. That's a good junction. That's open. That transistor seems okay. No, this one's bum. This one's done. Yeah, it's shorted. Shorted. Okay, that's the bad one there. Let's try some of these other ones. It's good. Suspect. Suspect. Let's try one of these. It's good. Suspect. I don't know. Be putting some transistors in this thing. So I managed to unbolt the heatsink assembly and it's free, except for the 2 temperature switches in the bridge rectifier. I have to remove those, so I'll do that. don't need to do that on camera. Okay, I got all the thermal cutouts and the bridge rectifier removed. I can remove the heatsink for cleaning. You can see how dirty it is. I'm wondering if this was, I don't know, there's a lot of corrosion on all the fasteners. I'm wondering if this was a coastal unit, but that's got to be all cleaned. Put that aside. And we can see all our transistors. We got 4 NPN, 4 PNP, 4 NPNs, PNP, NPN, and these 4 here. I don't know what they are. They might be drivers. I'm not sure. But let's get a meter out and do some tests for short circuits on the outputs. So far all good. No shorts anyway. Which is a good thing, which saves me from buying all new transistors. I think we have them all good. But I'm gonna pull all these and we'll test them on a circuit just to make sure that they're all good. Alright, looking not bad so far. We just have a lot of heat damage, a lot of cooked parts. I wonder, I don't know, I should be able to work on this board with it in the chassis. I don't think I have to remove it. Well, no, that's not true. I have to remove it. It's got to come out sooner or later, so I might as well do it now. Got AC line fuse, 7 amp, 120 volts, low blow. And what do we got? We got a 32 volt fuse, which is wrong. MDL 10 amp fuse. That's incorrect. Okay, first thing to come out is the fan, and I think it's scrap metal. Those crunchy noises it makes. That's not cool. Let's apply 12 volts and see if this thing spins. Which is positive, does it say? Can't see, it's all dirty. Doesn't matter. Ooh. Still working, that's unreal. The fan is probably okay. I don't know. We'll see. I'll have to think about this. This might just go in the garbage. The bad thing about the solder sucker is it leaves all that lead poisoning all over the board. All that fine solder. Just keep going here. We're going to take all the transistors out. And then we can start determining what's wrong with the circuit. And then we can build it back up from there. I don't need to take the transistors out. I prefer to do it because I could test them on a circuit, and then we know for sure that we have a good match set, or a good set to say the least. Yeah, I just want to make sure it's all done right. Lots of damage. Wow. And get over all the heat damage on this thing. This whole area here is messed up. This area here is messed up. This area here is messed up. Somebody marked these two transistors XX and they desoldered them. And I don't know. These are TIP 35s. So, nice thing about this is it's all easy to get parts. We have 2SA1302. And I think we have a, I can't remember what the complement is, but pull one of those out maybe. 2SC3281. There's our complement. I think we have 10 pairs of these. So it could get expensive if you have to replace them all. Alright, I think I got them all. Some of them I still need to work on. Okay. Yeah, somebody's definitely been in here before, marking things on the board. Okay, here's the final tally. So all these output devices were okay. We have 3 that are low in HFE. They're the outliers in this group. And the PMP's ones are all good. These are the TIP 36Bs. There's 2 of those. They're both fine. These 2 are dead. These are the TIP 35s. 35B. I haven't looked at the schematic yet. I don't know what they do. So these are easy to get. These are like $1 each. These 2 I'd like to, or these 3 I'd like to replace, but I only have 2 in stock, so I might replace just these 2. I don't know if there's any real advantage to it though. I'll have to check and see what the minimum HFE is for these devices. And we'll take it from there. I might replace them, I might not. Alright, this heatsink here and these insulators doesn't look like there's very little, there's really nothing on them. They're dry. They have an oily film. Like a very, let me get a rag here. Very light. There's really nothing on them. So I don't know what was, you can see. I don't think it's been disassembled before. Maybe it has. Didn't look like it was. But there's nothing on there. Everything is on the other side. So maybe somebody did have this apart once upon a time. I don't know if that's mica. Looks like it might be mica. Hard to say. But it's stuck down with something. There it is. Yeah, these are mica, I'm pretty sure. And that's the original. So we're going to have to repaste all this anyway. So what I'm going to do now is I'm just going to go through with a multimeter and start checking devices. I'm going to check these transistors, these ones here. I'm looking for shorts. I'm looking for any bad parts. I have to replace a whole bunch of resistors. Here's one that's toasted. And there's some down under here that are toasted. And then replace all those. And I'm going to make a list of all the parts I'll need. Here's another one that's burnt up. Another one that's burnt up. Yeah, there's a lot of damage on this. So I'll go through and make a list of parts I need. I need to get the drawings from the schematic and the parts location because nothing's marked on the board here. And then I'll get this list assembled. If I need any more semiconductors, I'll order them now because I need to put an order in, and we'll do that. And then aside from that, the only thing I need to do is replace caps. A lot of these caps are probably going to be toast. Look at these ones here. They'll probably be all toasted. There's quite a few all over the place. Yeah, so I'll make my parts list up and see what we can get going here. This board here is the Triac control, and this is a form of Bob Carver's invention of regulating the primary side of the power supply to keep the secondary in line with what it needs. It kind of throttles the power going in. That's what it's for, in a simplistic way of explaining it. And if this is all working good, that's a blessing because you know, a lot of people have problems with these, and it's really not that hard of a circuit. It is a multivibrator, some transistors. I believe, well, maybe I'll shut up because I didn't really look at the circuit, so I don't know. So that looks like it's working okay. I don't see any burnt up parts here. burnt up parts are all over here, 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 and throughout the thing. So I'll get busy on that. I have some op amps too. I don't know if they would be fried or not. Another thing I'm going to need to do is find a low voltage power supply. I'm going to get rid of this garbage, and I'm going to replace it with a proper computer fan and a fan controller, and we're going to use that to throttle the fan according to how much heat is being generated. So we're going to go that way instead of using that thing, and hopefully it should be a bit better. I'm assuming all these caps down here would be fine. I might just leave them. I'll pull them and test them maybe. I mean, they're going to need cleaning. Everything's filthy in here. It's pretty dirty. Yeah, I don't know who designed this thing, but it is not built for servicing. So I'm trying to get the main board out because I got a lot of work to do on it. And so far I've had to remove the filter caps from their mounts just so that it clears, and removed all of the screws. So I'm able to lift the board up to this point, but I can't get it past this corner. This corner is hooked right here, and this corner is hooked too. The board is too wide to fit within this confined chassis. Can't get it out. Fight with it and curse, and yeah, I don't know what I'm going to do here. I think I'm just going to have to take the whole thing apart, because that's what I'm trying to avoid. I want to leave the chassis with the transformer and its power supply all intact, and I just want to get the board out, but it seems impossible. So I'll have to, I don't know what I'm going to do with this. You can't pull it out this way. It's hooked here. And there's just no room unless I bend the board. And I don't want to bend the board. You can't bend the board. Get this aluminum plate here. I'm going to have to remove the front. That's, okay, that's a little easier than I made it out to be, because I just had to remove 2 screws and this side separated. That also makes everything else fall apart. Look at the corrosion that's going on inside here. I'm noticing on all the fasteners there's corrosion. This must have been a damp location or something. But I don't think any of the electronics have been affected. It's just a matter of maybe putting new fasteners, screws. But I got the board out, and we can now have a good look at all the damage to it from the heat. So we're going to have fun reconstructing this. I already have some ideas on this reconstruction. This part here I don't really care about. This is dropping resistors for the fan. We have a different solution for the fan, so I might just eliminate all that and get rid of all that. But now I can go through and check components and make sure they're all good and replace capacitors. I don't know if I'll replace these. They'll probably test fine. Capacitor banks, these are 1000 mic each at 63 volts, and this is 2200 mics each at 35. So they got 2 low voltage supplies here. I think one's 59 volts, one's 27, I believe. And then the main rails is plus or minus 97 volts with the main filter caps. So I think we have 3 separate voltage rails, or sets of voltage rails. Okay, I'll get started on this. I got some black glue in here. I don't know why that component. Here's some more black glue. It's all dried up. So I'll get busy on this. I don't know what I'm going to do with this thing. Clean this up as well. I'm going to test these caps, make sure they're 100% before we go any farther. And then it's just cleaning everything up. Everything's filthy. Dirt and corrosion. That's the theme of this one. Alright, the closer I look at it, the more crap I find. So these caps aren't great. They're baked. These are only 85C caps. This is probably the best one so far. It measures about 950 microfarad, but it has twice the ESR what it should have. This one here came out in pieces. I don't know if you can see that corrosion. It spilled its guts on the board and it leaked and it corroded the pin. I knew I smelt kind of electrolytic, you know, aluminum electrolytic. You can smell it. It smells like dead fish almost. And this had a strong smell to it. And obviously this is the reason why the caps are leaking. Let's keep going here. I don't know. I'm trying to get a take on the damage that's caused. Let's try this. Let's try another one. If I can get it out. Let's see here. I need the silicone they used is doesn't stick too well to the caps. That's a good, so you can actually pull out big chunks of it. But it sticks to everything else. Okay, so let's pull this cap out. Okay, here we go. Oops. Well, that one came out. In grand fashion. Somebody's been putting their little signatures on it. 11 of, I don't know. So let's check this one. Yeah, this one's a little worse. 940. And it's 100 milliohms ESR. So all these caps are going to be let me try another one. Let me try one of these. If I can get them apart. Okay. Let's take this one out. They're all going to get changed. I'm just checking to see how bad it is. This one's a 2200. And it's measuring right at 2000. Still got 70 milliohms ESR. That's not cool. For a 2200 at 35 volts. Yeah, well, it's actually not bad. Not bad, actually. It's one of the better ones. Alright, update time. So I'm just going through the board here and I'm just replacing burned out parts, or dead parts, parts that I found are defective. I went through and did recapping. I'm still waiting for these caps to come in. Probably waiting another couple weeks. But everything else has been replaced, with the exception of this here. I'll talk about this later. A lot of the caps are completely dead. Like if I put them on my cap measuring machine, they measure like picofarads, open circuit, kilo ohms in ESR. So they're all burned out, just burnt, just baked. And surprisingly enough, I haven't found any dead semiconductors aside from those two TIP 35s. Were they here? Here, I think, yeah. And it's kind of interesting to see where the failures are in this. Once I start going through it and I'm just tacking off which parts I've been replacing, and I can show you the areas where the damage has been and where it seems like everything else is fine. I think the amplifiers are fine. Let's go through this. Okay, I hope you can see all this. This is a lot of information on this page, and it's not a very good scan. I got this copy of the service manual straight from the Carver website, and it's slightly better than the one at Hi-Fi Engine. The one at Hi-Fi Engine is pretty much useless. You can't even read it. but this one's a little better. You can blow it up and you can see a few things. So areas marked in green are potential, well, they have been damaged by heat. We have these two transistors here and here. We have all these resistors and caps here, and all these resistors here are burned out. There's 4 of these circuits, and each of them had a resistor that tied to ground that was overheated, so I replaced those 4 as well. So the 2 TIP35 transistors are here and here. Now what these 4 circuits do, there's 2 for each channel, one for the positive rail, one for the negative rail. And what they're doing is they're supplying this with, for example here, plus 56 volts and plus 97 volts. And the purpose of this transistor is to switch this 97 volt rail in and out when it's needed. Typically the amplifier runs on plus 56 volts all the time, and it goes through this diode and then it goes through to the amplifier. Okay, and then there's plus 97 volts with this transistor that gets switched on when it needs to. I still haven't figured out how they're doing that. There's something with these lines here that goes to this op amp. Not sure what they're doing with that. But when the amplifier demands it, I think, this 97 volt rail comes in play and it goes through this transistor. Now these 2 transistors were shorted, I think. Shorted or open? I think they're shorted. I don't know, I can't remember now. But that was messing up these voltage rails on these both channels. Another area where all the damage was, let's see here, I'll show you on the board. This area here, this is right here. This is a power supply for the fan motor. It comes off of here, which is AC. This is AC here, and it sends AC up and it's rectified, and there's a bulk capacitor here, 2 dropping resistors before it goes to the fan motor. These were all burned up. Okay, we're going to eliminate all this altogether. We're not going to have any of that in our future amplifier. These 4 resistors here we replaced. I upsized them to 2 or 3 watt. These are 3K at half watt. They were all toasted. These 4 resistors were toasted completely, so I upsized the wattage on these resistors. Okay, that's a pretty simple fix. This power supply here, this is this part, and this is all toast. It's all baked. Dead resistors, dead caps. I've got a couple Zehners. Everything's got to be rebuilt in this area. And that is this here. This comes from the plus and minus 97 volts and the plus and minus 27 volt supplies. I don't know why they have both there. Maybe one's a bootstrap. But they run it through these resistors, and then they Zener diode it to regulate it to 10 volts, plus minus 10 volts. So this supply was completely baked and burned out. So we're going to have to rebuild this. Other than that, everything as far as I did testing is semiconductors, resistors. Actually, I haven't done resistors yet, but I'm going to did the semiconductors. They're all fine. They're all fine. We pulled out all the output devices and tested them. We saw they were fine. So basically the troubles were in the power supplies. Power supply plus minus 10 volts. This is for supplying op amps, I believe. And then the power supply for the fan was baked. And then these, I don't know what you'd call, they're not power supplies, but they do switch rails for the amplifiers. They had 2 baked transistors in there. So that's basically all the damage there is. Now I said I'm going to eliminate this, and I will. I'm going to take power from this transformer. I don't know what voltage it is. If I measure it plus minus 27 volts, I think I did the math, it's probably quite high. But What I'm going to use for a fan controller is one of these Chinese controller modules. These are temperature, they're programmable, and they have an alarm. Here's a temperature sensor. And feed this with 12 volts, and then you can run 2 fans off this if you need, or 3 I think. And it's adjustable and programmable. And I've used these before, and these are great because you can select what temperature range you want it to go up to before the fans go on high. And these work pretty good. Now, for the heatsink itself, they had this goofy fan on the end here, blowing on it, or sucking, or whatever. Probably did suck pretty bad. But I'm going to get rid of this, and we're going to use some proper computer fans. These are 12 volt fans, almost 10 watts. So the draw is nearly an amp. I was thinking of mounting one of these on the end of the heatsink, blow all the air across and keep it cool with the temperature sensor module that controls it. Now I need to figure out a 12 volt source for this thing because this is all running off 12 volts now, and that's why I was thinking using this here, tap off here, and then I can either use a dropping resistor or something to bring down the voltage and have a 3-terminal regulator just to keep it regulated at 12 volts. 3-terminal regulators are good for 1 amp. This fan's going to draw about 1 amp, and everything should be good. And this thing will not turn on until it hits a certain temperature, and so that keeps everything quiet, and also saves a lot of energy too, because we're not going to have all this garbage here cooking away at the board and creating heat. And from the looks of this, the fan was on continuously. There's, I think that's a 50-degree switch, I'm not sure, but I don't see it in the circuit. I don't know where it is. It might be in the wiring. Yeah, you know what? Now that I think about it, this is a 50-degree switch, and it turns on when the heatsink hits 50 degrees, and then the fan kicks on. So the fan's going to cycle on and off when this is 50 degrees. But looking at how burned out and worn out this motor is, and how dirty it is, it's seen a lot of heat throughout its life. Like, it's been cooked. So we're going to eliminate this and use a proper server computer fan. These are really high quality, and they run quiet, they move a lot of air, and they don't suck much power. Well, they do, for considering how much air they move, but they work pretty good. So that's my plan. Right now I'm waiting on parts. I'm waiting on these 2 transistors to arrive, and I'm waiting on a couple caps I need to replace in there, and then we can button this one up. So I've been working through this, just replacing caps so far. I did that yesterday, and I gotta say, this board is not very good. Wherever the heat's damaged the board, the traces automatically lift. Like all these traces are gone right here, and there's really nothing holding them down anymore. So that's why I'm eliminating parts of the board. This is another part I'm going to eliminate. I'm going to eliminate all these traces. They've all lifted. I think if I could go under here, I can lift some of these coppers. Anyways, I'm going to eliminate all the circuitry on this board, and I'm going to build it probably on some posts or turrets. I'm going to mount some turrets here, and I'm just going to build the circuit up in the air. So it's not even touching the board, it's going to be up in the air, it's going to have full airflow. A lot of that I'm going to have to do because I'm not interested in repairing burned up printed circuit boards. Now you can probably see I've already put bodges here for some of the traces that lifted, and these are just insurance to make sure that the trace is lifted. See here, right here, you can see the trace lifted. Let me zoom in. So I don't know if you can see this trace here is lifted. So that's why I had the bodge wire. This is a backup security. If this trace were to break, then they got the backup wire. So that's why I'm doing the bodge wires. And if I see any spots where pads are lifting or traces are lifting, I'll back it up with a bodge wire. And I've done a couple of these already. Where are we here? Oh yeah, I've done some down here. Done these ones. These 3 pads are bonded together. These 3 pads are bonded together. And that's to keep it reliable, because once we put it back in service, it's going to start heating up again. And those pads can break, or those traces can break. So yeah, I'm just, like I said, I'm waiting for parts. Probably put this aside and work on something else in the meantime, but I don't think it's as bad as it first looked. I think, you know, all the damage is to the power supplies, and that's just from being baked, turned on continuous for thousands of hours maybe, I don't know. Capacitors are gone, and we're going to get this thing back together. Okay, time has come. I have to deal with this issue here. This is completely trashed. So this here is, let's see here, is this little circuit here on this circuit. There's a plus and minus 10 volt supply that supplies the op amps. And it's dropping resistor, Zener diode, capacitor. It's pretty simple. And there's 2 of them, one for the plus, one for the negative. And I'm going to build it right here. I'm going to strip all the parts off here, and I'm going to build it right here. What I'm going to do is, I bought these on AliExpress. These are turrets. I had a hell of a time trying to find them. I was looking for posts, searching for posts and standoffs and all kinds of terms. Nothing come up. And then it finally, I came across a turret. And it's, what it is, it's like a little post. I don't know if these are gold plated or just brass. This is an M2 turret. Okay. I tried to get the smallest size I could get. So what you do is you drill a hole through the printed circuit board, and you use your nut and washer to secure it, and it stands up. I can drill holes wherever I want these turrets, and I stand them all up, and then I can just tie my parts to them and solder it all together and build the circuit. It's going to be built off the surface here by about 1 centimeter, and that will get all of the heat components off the printed circuit board and up in the air where they can get circulated air. And yeah, so we got 2 Zeners, 4 resistors, 2 caps. I'm going to strip all this off, and we're going to get this completed. I don't know what I'm going to do about this part here. This is something else, and it needs to be moved or repaired or placed somewhere else. These resistors, I don't even know what they are. We'll figure that out. But I'm going to get down to business. One thing I need to do is flip this thing over. And you can see this side is pretty scorched. So what I did is I took a photograph of the scorched area, and I need to figure out grounds, and I need to figure out supply points. I think supply points are here and here, and I think this is a ground. And then I have to figure out where the 10 volts goes out. I know this is a jumper here, there's a jumper, so this is 10 volt, and that goes off to the circuits. And then I think there's another one somewhere up here, but we'll have to figure this out and get this all laid out. And then I'm going to strip whatever copper I'm not going to be using. Some of it will stay, some of it won't, but most of it's going. And we're going to get this sorted. We have to build that circuit right up on this, and I'll bring you back in when I've got some progress. Okay, time for a bit of an update. I've been doing a lot of work behind the scenes here, and I haven't been filming it, but got quite a bit done. Let's see, I got this circuit here almost be rebuilt. This is what it's going to look like. It's sitting up on turrets. Here's the underside. There's really nothing going on here. I removed a lot of the traces because they were just in the way, and I made connections where I could with copper foil, and this area here is really weak. It's soft, like the fiberglass resin is completely gone in this area. So you can see it's got a lot of give to it, and it's not quite sturdy. So I'm thinking maybe when I'm done, I'll coat the back side of this with a UV resin and just cure it, just so it gives it some strength and protection. Some of these foil traces are floating in the air, and I want to protect those. So that's happening there. Now I could lock these in place with the resin as well. I think I'll do that. But I got this built. This power supply is built. This one I haven't wired up yet. There's let's see here. Where's my? If you look here, we have 4 supplies. We got plus and minus 13. Plus and minus 10, and they all come off of the plus 27, minus 27, plus 97, minus 97. I haven't found those resistors on here. I don't even know if they have those resistors in place. There is a 27K, it looks like, and 5.1K 2-watt resistors. I don't know if they exist, but I'm going to build this circuit. All I have to do now is connect it up to the rest of the board and ensure my wiring's all correct, and check my connections. I've gone through, I've checked all these 4 op amps. Okay, they're all checking fine. All the caps were replaced. The capacitor banks have been replaced, so these are ready to go. Yeah, I just need to get the connections of these power supplies wired in, and then I can probably put the board back in the chassis. I think we're done to that point. I don't think I have anything else to do aside from maybe cleaning the jacks and switches. I haven't done that yet. I don't know if I can clean these. They're pretty tiny. We'll see. Everything else checks out. Parts are starting to come in. Got my new transistors, got some other stuff, and that's all ready to go. So let me wire this in, and then I'll bring you back when I got this back in the chassis. Alright, so I finished. I know it doesn't look like much. Actually, it looks like crap, but it's going to work, hopefully. Now, I have run into a few problems. A lot of problems dealing with just trying to build the circuit in my head and trying to 3D model it in my head and put it on the board. I screwed up and I mixed up my polarity on my positive and negative supplies, and I was dumping reverse voltages on these caps, which they didn't survive. So I fixed that all up, got it corrected. Now I got all my supplies. Let's see here, I can show you. Here's my meter. Now, one thing that really confuses me is this here. Let me show you. On this op amp U1, they have a positive 10 volt supply and a negative 10 volt supply, and then through this diode D5 they have a negative 13 volt supply, which pulls this down to negative 13 instead of negative 10. I don't know why they do that. So I'm going to show you right here on this this op amp. This is U1 here, down here, and what do we have here? We got, here's our 10 volts, okay, and on the negative supply we have negative, well, 12.6, 13. That's our 13 volt supply. I don't know why they do that. That's really odd to me. Anyways, these other ones are all fine. Here's plus 13, negative 13. This one over here is 10, negative 10. Got 10 and negative 10. So the supplies are working good. Everything's fine. Next step is I gotta clean the back of this board, and I'm ready to put this back into the chassis. All the caps have been changed. This power supply has been built. I want to tack down some of these wires. This wire here is going to be for when I put the harness back together. So looks like it's all a go. I checked all the op amps, they're fine. It's just a matter of connecting things up and getting things powered now. Just checking out the main filter caps here. What are these things? These are 9,000 microfarad at 100 volts. Minus 10 plus 75%. Okay, so here's what the first one measures. So we got 7,000 microfarad, that's more than 10% down. And we're at 159 milliohms. Yeah, look at this one. This is the capacitor for the positive rail. And we have a problem here. We have 2.4 microfarad, 10 kilo ohms ESR. So this capacitor is completely open and dead. So I might as well replace them both. Now I wish I would have tested these weeks ago, because I could have had parts ordered and I had it here by now. All my other parts have come in and I thought it was going to be easy peasy, just put it all together, but no, I didn't check these. Now I have to order parts and wait for those. So I'll see what I can find. These are an unusual case style. 100 volts minimum. I'd like to measure the rails. It says plus or minus 97 volts, but I have a feeling it's probably higher than that. So maybe I'll see what I can find in this case size, or maybe something smaller. Shouldn't be too difficult. Yeah, look at this, it's been leaking. I think that's been leaking, I don't know. It's really not a good cap anyway. Yeah, when I test it out of circuit, look, it even gets better. We got 240 nanofarads and it's a 35K ESR. Wow. Okay, I'm just getting ready to wrap this up. There's this board, get it ready to be put back into the chassis. I'm tying up some loose ends. And I already cleaned these two pots with 401B and followed up with deoxit fader lube. It's not fader lube, it's F100. And they should be good. Now I'm looking at these two switches. I measured some contact resistance on these and they're up around 100 milliohms. Actually, one of the switches is up around 2 or 3 ohms and then the other one was 100 milliohms. So I tried a treatment of the 401B from MG Chemicals and it didn't really seem to clean it up at all. It really didn't change the contact resistance. So these two switches, one of these is pretty important. One is the bridged stereo mono switch, bridged for the amplifier. So this one, I don't know which one it is, but one of them sets the amplifier up for mono block mode, and the other, when you have the switch out, it's in stereo mode. The other switch disables the clipping indicators on the front panel. I don't know why you'd want to do it, but there's a switch for it. But these two switches aren't very good. So I have options. I have new switches I'm going to replace. These are pretty much equivalent substitutions. I buy these on AliExpress. Please don't ask me for a link because I don't have links to this stuff. I just go on AliExpress and search for push switches, double pole, double throw, and you'll come up with lots and lots of variations of switches, and these are just some of the ones I bought. They're cheap, but you know, they do their job. They're switches, and I think they're both equivalent to each other. I think they're pretty much identical, just different manufacturer, but they have the same dimensions, partially because this is like a standard switch in the industry and you can buy these. So yeah, if you want to replace these switches, go look on AliExpress and you'll see them there. So I think I'm going to go with the gray ones. I don't know what the difference is, to tell you the truth. I don't think there's any difference, but we're going to replace these two, so I'll take them out and get these new ones in. Where's it sitting on? see if we can get this one out. Okay, one's out. Okay, clean this one up as well. All right. So as you can see, they're probably identical in every way. They line up that way and they line up this way. I'll pull these buttons off. And there it is. Actually, the plunger's a little farther, a little longer than the original, but whatever. As long as it works, we care. That's all we care about. So let's put these in, and we'll solder these up. All right. Alright, we're all done. Clean that up, and we got 2 new switches installed. So thanks to DigiKey's overnight shipping, I have new caps in my hands. Let's pull them out and make sure they're going to work for our application. Okay. Alright. I love the way they overpack everything. So, oh, got those nasty stubs on the back. Whatever, we're not going to use that. But this is our replacements. Now, the reason I have these because they're same diameter, a little bit shorter. We have our same thread, screw terminals. These are rated at 100 volts DC. Now I looked at the data sheet for these, and these are tested at 15% over voltage. So they're good up to 115 volts DC as a surge. And you can do that so many thousand times before it might fail, who knows. But this should work in place of this. Now, these are 9100 microfarad, these are 9000, same size, pretty much. But I'm looking at this, and why did it fail? Like, look at this. Look at this cap. It's dirty, yeah, we know that. But it looks pretty normal. This one's still working. This one's not. Look at how gnarly it is. It's got all kinds of bumps and weird stuff going on underneath. Like here, like look at that. Can you see all those bumps and stuff? Let's open this thing up and see what's going on with it. I have a feeling that the can failed and allowed the electrolyte to leak out or whatever, and that's where the leaking's coming from, is the can itself. Let's see if we can open this thing up. Oh yeah, look at the corrosion under here. Should be wearing gloves. It's actually wet with something. Oh, it stinks. Oof. Wow. That stinks. Ugh, I shouldn't have done that. Oof. But we can see the failure of this thing happened. I don't know if it was the seal or if it breached the can itself. Looks like right here somewhere there might be a hole. Should be wearing gloves. Anyways, this is garbage, this can. So, straight to the garbage. Okay, I'm just installing the new capacitors. And one thing I noticed right off the bat here is their use of these these lug terminals. I'll tighten this one up as well. Let's do them all. Stay away from that one. Okay, you notice that the solder between these two have broken, and there's actually a broken connection between the two caps now. So when I get these caps in place and mounted, I'm going to go through and resolder this connection, because that's kind of important. You don't want to have a broken connection on this is the ground leads for these two caps, center point. So pay attention to that. Okay, I got the capacitor mounts in place, and I double checked the terminal connections. They're tight. So we can start zip tying these in place. They go like that. Okay. We need zip ties. So let's get some zip ties in place. And we'll get this. Okay, let's put this one in first. Actually, you know what? I'm going to leave this sticking up. Let's get zip ties in the other one too, because I think there's probably a sequence to doing this. If we screw it up, then we're going to have to cut all the zip ties and start over again. So let me get this one in. Like that. And get this one in. This out of the way. Okay, I think we're ready. So put this one in place, and then this one in place. Okay. This one. Where's the other side of this one? It's hiding underneath. Okay. Let's get these two. Okay. Now we can get these positioned properly. About a centimeter between that and the transformer. Tighten this one down. Okay. All right. We are together. Let me cut off the excess. Secure. these. I think I might just go up here. Out of the way. Now we need to resolder this connection. This one is bad. And you can't see it from where you are, but I can see it here. Surprising they did this with these solder lugs, because any movement between the two caps will end up cracking the solder. Solder is not very strong. It doesn't have a lot of strength. It's pretty soft metal. Just going to make sure that joint is hot and it flows. Oops. Yeah, that joint is hot. Alright, complete. Caps are in. Okay, I think I'm at the point where I can start putting the power transistors back in, and we can get this thing going. I have all the wiring completed except for the fan wiring, which I deleted. I pulled it out. This is the thermal switch for the fan and the wiring for it. Yanked it out. We're not going to use it. We're not going to use the fan. We're going to develop another solution. But this thing is quite interesting. I was going through the service manual, reading the text on this amplifier. What it does is it regulates the power going into the power transformer. It has a circuit down here in the bottom that senses the rail voltages, and when the power amplifier starts working hard and the rail voltages start to sag, this little circuit down here, there's an op amp and an adjustment, and this gray wire, you see this gray wire here, this gray wire provides feedback to this opto isolator, provides a signal, and as power sags in this circuit, turns on this opto isolator, and this triac circuit, when it senses the opto isolator coming on, what it starts doing is it changes the phase angle of the trigger for the triac. So it starts triggering. So what, like, well, let's start again here. When there's no load, the triac is triggering on a very on a phase angle that produces very little power going through the power amplifier or the transformer. As we start loading the amplifier down with more and more signal, and the rails sag, the triac conducts later in the cycle and provides more power going through the transformer, which in turn bumps up the rail voltages. So it's regulated that way. It's kind of interesting to see in the service manual how they had it written up there. There's a whole description written up on how it works, and it's pretty interesting because, you know, when you're listening at normal levels, this thing probably consumes very little power, but when you crank it up, it allows 350 watts per channel, which is amazing. And I think there's a lot of iron here in this transformer, but I think it also is probably a little underrated transformer. So what they're doing is they're overdriving it just for the times when we do need 350 watts per channel. So it probably works great for music where there's peaks, and for the most part music's not that loud. If you're going to do continuous tones, this circuit here probably be under a lot of stress, I'm guessing. Don't know that for sure, but we'll see. So I have to put the transistors back in. The two TIP transistors go here, and then the other devices I'll go back and I'll put them all in. I have cut a couple of little foam blocks. This is soft foam with a single adhesive on one side. If it comes off, it's not going to play nice as soon as the camera's on. Anyways, this will go under here, under this transistor, and it'll provide a soft kind of a spring to keep that transistor up in the air. and contact it with the heatsink. So I'll put the other one in. There's another one here. I'll put them both in, and we'll get this thing loaded with transistors. Alright, transistors are in. I tacked one lead down on each transistor, so they're not soldered in place, they're just tacked in by one lead. And this allows me to move them around, and I'm going to paste them up now. And then once I install the heatsink and bolt it down, then I go back and I resolder all the connections on the back of these transistors, just so that there is no stress on the lead after tightening it down. If you solder all the leads now and then go in and tighten these 5 bolts, you'll put stress on the leads and the pad on the printed circuit board, and you can actually rip a pad off if you push a transistor down when it doesn't have the room. So that's why I bolted down first and then resolder. So I'll get busy pasting. Here's our 2 new transistors, and I'll get busy repasting these with thermal compound, and then we'll put it all together. Okay, the heatsink's bolted on. I gave about 10 or 15 foot-pounds of torque on these. Don't have to go crazy on them there. But you want to have them pretty tight, because you want the heatsink to clamp down on your transistors. Now, looking here, I don't know if you can see this, I hope you can. Put this so you can see it. You can see the heatsink compound coming out on each transistor. There's a little bit squeezing out on each one. That's what you want to see. You want to see those transistors making contact, and you want to see that compound oozing out as you tighten it down, so you know that you have a thermal contact. So this is all bolted down. Now it's time to resolder all the connections on the back. All these connections need to get resoldered properly. Now what I'm going to do is the first joint you want to heat up is the joint that you soldered previous. You just want to see, and then you hear a little click. I'll do it again here. Hear a little click. That means you're relieving the stress. As the solder melts, the stress gets relieved. Ooh, there was a big one. Yeah, you want to be careful with these. You don't want to pop a trace off. This one didn't have any stress. So I'll go through and I'll reheat all these joints, and then I'll solder up all the remainder joints. And then we're ready. Alright, this is the moment I'm dreading. This is the time to do the power up. Now, this first power up. Now, there is a procedure in the service manual for doing power up after service, and it's pretty simple. They want you to have a scope, an isolated line triggered scope with no secondary ground reference, because you're going to be probing around in the primary circuits. Now, I don't have an isolated probe or a differential probe or whatever you want to call it. What I'm going to do is I'm going to scope the secondary that comes out, because it should be the same signal, correct? Or close. Primary signal, secondary signal. I got a probe here, and it's right on this winding that's coming out of the transformer, and it's referenced to the ground, so I can see on the scope what's going on with the transformer. Now they want you to set the controls RP100, RP200 to minimum counterclockwise. So I did that. Oops. I went under here, and these 2 trim pots set to minimum. They want you to set RP1 to minimum. That is the voltage regulator pot, and that is set to minimum as well, fully counterclockwise. Set your level pots to clockwise, full. Okay, they're up. Then you plug in your unit to variac and power up the variac until the optocoupler conducts at approximately 85 volts AC line voltage. So I have the variac set up, and I can turn it up from 0 all the way up to wherever we need it. So I'm going to monitor what's coming out of the transformer, and once the triac starts firing and the thing comes alive, we have to confirm some voltages. We have to confirm our plus and minus rail voltages here, which should be about 75 volts plus and minus. our other voltage rail, which is plus minus 59, I think, or 657. That should read plus minus 43, and that's at this capacitor bank back here. And then the plus minus 27 rails should read around 21 volts plus minus, and that's on this capacitor bank here. And then we confirm that we have proper voltages on our op amps. And if everything looks good, looks like we're home free. So let's try this. I'm going to set you up on the scope, and then I'll bring this thing up on the Variac. Okay, I think I'm ready to do the first power up. We have no signal going in, so we're not going to test for signal. I'm just going to check for function of the power supplies here. So let's get our meter ready. I don't know if you can read that. Yeah. Okay, let's start turning it up. You can see the scope, and I'm going to slowly turn it up to 85 volts. We'll see what we get on the scope. So here we go. I'm at now about 70 volts. You know what? I have no fuse in this thing, so excuse me while I put a fuse in and turn the power switch on. Dumbass. Okay, you still with me? Fuse is in, power switch is on, let's start turning it up. We're getting some triggering going on here. It doesn't look like much. We're at 72 volts. 90 volts input. Looks like our track is triggering. Okay. So I'm at 87 volts, consuming 1 watt, and we are starting to get lights on our front. So I'll just keep going up. Just going to leave it here for now. Let's confirm some of our voltages. Let's do this one. Negative 27 there, that's not good. Positive 27 there. Where are these ones? $15. Negative 15, okay. So we're still low quite a bit. 88 volts. Our voltages are low. Just wonder if this has any effect on this adjustment, has any effect on. No, it has none. Let's see this one here. 7.5. Negative 7.5. We have voltages, but they're all low. So I'm wondering, let's turn this up some more. No, that's not what I wanted to hear. What happened there? Let's reset it and bring it back up. It's not playing nice. I'm going to bring it back up again. Seems we're going into full. Let me measure this voltage as it does that weirdness. Still have a problem in the regulators. So This cap was up. Yeah, 65 volts. What is going on here? Let me do some checks. Okay, I think what's going on here is the regulator circuit is not working properly. This opto-isolator has an LED in it, and when this circuit here senses a drop in the rail voltages, what it does is it sends current to that LED to turn that LED on, and when that LED turns on, this causes the track to change its conduction. Now let's monitor this LED right here, right now, and I'm going to slowly turn it up, and you'll see as soon as it hits the 1.1 volts or so, it goes into heavy conduction, and the power supply goes full throttle. That's what's happening here, I believe. So let's turn this up. Okay, voltage is starting to come up, 0.9 of a volt. We're at 1 volt, just about. Getting closer. 1 volt. Come on, baby. And it starts conducting. And I can turn it down. Yeah. So I think we still have a problem here, either here or here, with this regulator circuit. So I'm going to have to check this. It's a feedback loop, and it all has to be working before it's going to be. So let me dig deep into this. Okay, have a look at this. I'm scoping the input to the optocoupler. So this will be the voltage that the LED sees, and I'm going to slowly ramp up the line voltage. I'm at 0 now. I'm slowly going to ramp this up. You're going to watch, see how it's. I can turn down this speed of the scan so that it makes it more visible on screen. So let's turn this up. Right about there, I get a bump. The voltage is coming through. Another bump when I keep increasing it. If I keep increasing, get little bumps in the. Now when I increase it to the point where it starts conducting, this signal should, see, it's not self-regulating. That signal should be dropping off to allow the power supply to regulate, and it's not regulating. It's just giving a full-on signal. Yeah. And it's not regulating. So the problem lies in the primary of the circuit. Let's dig deeper into that. Okay, so I think the problem lies in this circuit here. Now this line here, WP, I think it says WPGRO. This is the signal that goes to the optocoupler. This is the signal that comes in on this line here and turns this diode on and off. Okay, there's our optocoupler. And it's WPG, WPO. G is ground, I believe. O, I don't know. But, you can hardly read this. But, this circuit here senses all of our supply voltages. And then it gives an error signal If it's low, it probably turns this LED on, and if it's high or normal, it either strobes this LED or turns it off. I don't know yet, but something's going on wrong here, and need to figure out what it is. It might be that I just don't have proper voltages at U1. U1 is this here. Remember I was saying it's 13 volts here, negative 13 on the pin 4, plus 10 volts on pin 8. Why is this not working? So I'll have to troubleshoot this. Alright, so let's go through and see what I know and what I don't know. If you've done any work on switch mode power supplies, this will be right up your alley, because this is essentially what it is. You have a power amplifier, 2 power amplifiers here and here, and they're going to draw current, and they draw current from the transformer and the bridge rectifiers, filter capacitors. And as the power amplifiers draw more and more current with more and more output power, the power supplies will start to sag. And what Carver's doing here is they're regulating these power supplies with this circuit here. This circuit here senses all the power supply voltage rails, okay, and it goes through this op amp, and then it goes out in an output to the regulator board. The regulator board takes that signal, feeds it into optocoupler, so it's isolated, and turns this transistor on or off depending on what's coming in. And this circuit here throttles the power going to this power transformer. This power transformer is, let's say it's undersized and it's overdriven. Let's put it that way. It's undersized so that it fits in the cabinet. It's going to pass 700 watts of power to this, well, actually more than that. It's going to pass more than 700 watts, or volt amps, whatever you want to call it. But it's only sized, if you look at it, it's only sized for so big, right? And it can only put so much power through a transformer before it starts to overheat and burn up. But what they're doing is they're throttling the power to this transformer, and they're overpowering it for short periods of time, because they know music is dynamic, and it's not a continuous tone that you put and you're drawing continuous power through. Music is dynamic and it's varying, and you have bass notes and drum beats that require peak power. So that's why they can get away with doing this. So this side here, it throttles, turns on and off this triac, and throttles the power through this transformer. Now what that does is it greatly reduces the sag on these power rails. Okay. Now this is the plus minus 56 volt power rails. The amplifier uses plus and minus 56 volts during normal listing levels, but when we crank up the music and we want more power, these 4 transistors here kick in, and what they do is they switch in the 97 volt rail so that you get more voltage on your output devices. And then the same thing, if the power rails sag, then the regulator kicks in and takes care of that for us. So what I have a feeling is going on here is I'm getting I have to actually confirm all my power rails, but this circuit's all working, and we saw it when I turned it on. It's idling, and it's idle is feeding power through at idle, but then for whatever reason the opto isolator turns on, and with this circuit, and it goes full bore, like it wants to go full throttle on the power supply. There's no regulation here. It just seems like it's either one or the other, and there's no in between. So I have a feeling there's something wrong maybe with this op amp, or maybe I have a missing supply voltage. One of these resistors might be open and I might have a missing supply voltage, or there could be a bad component in here. So we're going to check this out. U1 is this op amp right here. So let's pull U1 out and test it, because I've tested it before, but maybe it's gone bad again, I don't know. So we'll pull this one out. Come on, baby. There we go. And we're going to plug it into this little op amp tester board here. Now what this does is just confirms that it's working. So if I put this in, it appears to be working. Now this thing's kind of confusing. It has some Chinese instructions. Something to do with these red lights flicker. I can see them both flickering. I don't know if you can. If I turn off the lights, maybe you can see them flickering. What if I block these ones? Can you see those red lights flickering? The one on the right is flickering for sure. The one on the left is flickering as well. But that tells me that the op amp's working. So maybe the op amp is fine, and we have a problem somewhere else in the circuit. We have to let me disconnect the power here before I set this down. Maybe there's a problem somewhere else in this circuit. I have a feeling that since I rebuilt these power supplies here, I might have a connection that's missing or something to prevent a voltage from appearing here. If that's the case, then it's just a matter simple of making sure these 6 voltages are here and then confirming that this circuit works. So we can do that. So the main problem I'm having with repairing this amplifier is the documentation. The scan on this is kind of poor. Even the one I pulled off the Carver website isn't the greatest. Now, for example, if I want to check these resistors, I have to figure out, okay, is that R28 or is that R20, 29, 30? That's what it looks like to me on here. 22, 23, 24. I can barely read these numbers. But where is it on here? I can't read any of these numbers. It's just a mess. I can see 24, 23, 25, 26. I can see these resistors here. But this is really slows me down because I have to find the component if I want to test it. I know what's going on in this circuit. I know what I need to look at, but to find it on here, and nothing's marked on the board, right? So everything is just a blind thing I have to work with. So I have to match component value with schematic, and this is the trouble I'm having. This is why it takes me so long. So I'm just going to keep plugging through here and see if I can figure this out. Okay, here's another interesting observation. I have the op amp removed, U1, and I got it powered on right now. And let's have a look at the waveform that's coming out of the transformer. So this is what's coming out of the secondary of the transformer. I'm going to ramp up the line voltage. Okay, the triac starts triggering. Kind of an odd shape there in the center. I don't know why it triggers on the positive cycle and the negative cycle. Maybe there's something wrong there, I don't know. But it does look odd. But anyways, we're going to ramp this up. And right there is full line voltage. And I guess that is normal. It's just flipped. It's inverted from the others, so it does look normal. But that's full line voltage right now, and it's just idling. It's sipping current. It's actually drawing. This is what the amplifier is drawing right now. It's 2 watts of power at full line voltage. See, we got 119 volts here. 2 watts. So everything's working on the primary side of the amplifier. It's just a matter of getting this feedback circuit to work with this op amp. Okay, I identified which resistors I need to measure. These 3 here and these 3 here. That corresponds with these 3 resistors here and these 3 resistors here. So we should have rail voltages on all 6 of these terminals, and I'm going to confirm that we do. If we don't, that's our problem. So let's turn the power on, and I'm going to ramp up. Turn power on, and I'm going to ramp up the voltage. Okay, I'm going to bring it up to 120 volts and then start measuring here. So what is this one? That's 36 volts. 21 and 10. Now you gotta remember these voltages are low because we are not, the power supply is not regulating yet. So these should be all negative on this side. Got negative 37, negative 37, and positive 37. Okay, should be negative 21, and this one should be positive. Yep. This one here, negative 10, and yeah, we had positive. So all those voltages are there. How about our op amp? Let's check our op amp here. Negative 27. Seems we might have a problem with our op amp power supply. So that is pin 8. Pin 8 should be positive 10, and it's not. Pin 4 should be negative 10, and it's not. Why do we got extra voltage here? 27, negative 5. Something's going on here with this power for this op amp. Let me take a good look at this. I don't think it's getting the correct power. Pin 1, 2, and 3, which is our pin 1. Pin 1, negative 6.5 mil. That's our output. That's our output. And then pin 2, negative 7.3. That's an input, and this is an input, 0.5. Okay, let me investigate this op amp power. Alright, what I found was this resistor here, it's almost impossible to read this schematic. This is R75 here, and it says 5.1 K, 2 watt, but it's not, it's 6.8 K. But this ties the negative 97 rail to the negative 10 rail. I think it's a pull down resistor. And it doesn't show it on this schematic, but it was connected to, this resistor was connected to the power for this chip, but it wasn't connected to the negative 10 rail, right? So there was a break there. When I did the conversion of this circuit here from this to this, I missed that connection. This connection comes in the top here, and it was supposed to come down and go up, but I removed all that, right? And this was floating, this wire. It should have been connected to the negative 10 right here. So what I did is I attached a bodge wire, temporary bodge wire, just for testing, and we're going to see if this is working now. So let's plug it in, try it out. Alright, so what I'm going to do is turn the power back on, and I'm going to ramp up the line voltage to normal, 120, somewhere right about here. Okay, the amplifier should be powered up, and it is. I got 117 volts going in, and we're drawing 2 watts. So I should have, on my chip here, I should have negative 7, and +7. That's a lot better. Okay, what I'm going to do is I'm going to power this down, discharge caps, and I'm going to put that chip back in. We're going to see how this works with that chip installed again. Okay, chip's back in. Now I'm going to do a controlled power up with the Variac, and we're going to watch on the scope. Keep an eye on the scope and we'll see how it does. It should regulate the so here we go, power's on. I'm going to start ramping it up. And I'm at 90% now, or 90 volts. Everything looks good. I'm going to go up to full voltage. And it started doing its thing again. Where are we at here? We're at 54 volts, 13 watts, 2 amps. That's a lot. This thing sounds really angry. I'm having trouble getting it over 65 volts. I'm at 70 volts, drawing 42 watts, 3.3 amps. I don't think we have a short. Let me check some voltages here. Okay, I ramped it up even farther. It's having trouble starting. It's at 97 volts right now, drawing 100 watts. I got negative 85 and positive 85 on the voltage rails. I'd like to know where this 100 watts is going. I'm going to shut this down. Let's do a little. Don't think we have. The heatsink was getting a little warm on this side. There's 100 watts went somewhere. I don't feel a lot of heat anywhere. I don't think anything's damaged by that. I think I'm just going to let it run like that, and I'm going to take some voltage measurements. I don't think we have a short. That's the problem. Where's all that power going? You have a problem with that circuit there, so maybe that's what the problem is. Let me do some more investigation. Okay, I got my blur out. I'm going to try this again. Ramp this up. Let's see here, I'll show you. Ramp it up some more. 100 volts. 89 volts, okay, 90 volts is starting to kick in. It's drawing 90 watts. If I turn it up to 100 volts, I'm getting 130 watts dissipated somewhere. And I don't really see, there's 3 components there. Most of it's coming out of the heatsink. You can see that where my hand is. I remove my hand, you can see the heatsink. Yeah, so where's all this power going? 140 watts. I was trying to get a fix on where this power is going. Our caps are cool. Everything on the Triac driver board's cool. All the power is coming out of the heatsink. Now I did check the outputs for any DC and it's 0. Let's see here. Yeah, it's getting quite warm. Has to be the transistors. Okay, I turned that down. Maybe I had this the wrong way. I got it now up at 115 volts. It's drawing 138 watts. And I'll show you the waveform here on the scope of our transformer. Okay, going up in power. Here we go. Tracks firing, and then it goes into now if I turn it up, it seems to be self-regulating. Let me see what I have for power on this, on the voltage on the main filter caps. I should have 97 volts. And I have 78. It wants to regulate to 79 volts. You see as I turn it up to maximum, see how the Triac is compensating. Now if I turn the adjustment, you can see it wants to go in full conduction. The power consumption goes up to like 200 watts. Definitely something wrong here. So just from that little bit of testing, our heatsink is already up at 45 degrees Celsius. Which is kind of interesting. I think there's something wrong. There's something wrong with the power amplifier. Let me go through and check all the output devices again. Maybe I found a problem here. Maybe I'll find a problem. I don't know. Okay, you want to know what the problem was? I'm a dumbass. That's what the problem is. Now I had the bias settings for both amplifiers turned to max, and I assumed they were turned down. It said counterclockwise. So looking from the front of the pot, I turned it counterclockwise, but that was maximum. So I flipped the pots fully to the other direction, and let's power it up and I'll show you what I see. If you can see this, let's go 85 volts, 95, and then it kicks in, taking it right up to 130 volts. We're drawing 12 watts of idle current, idle power. So let's turn this down to 120. And this app is live right now. And it's drawing 12 watts on 120 volts. Now if I turn up the bias trim pots, watch. See how it goes up? Yeah. So it's working, and I just need to get everything adjusted and confirm everything is working properly. We're going to feed a signal through. What I'm going to do first is I'm going to shut this off, and I'm going to fix up this bodge wire. I'm going to get rid of it and make it disappear. I'll put it in the circuit somehow so that we can't see it. Probably put it up top here. And then I think we're ready to do some testing. Thank goodness for that. Alright, so now we got past that hurdle. We're going to continue on now. What I want to do is I want to continue on with this power up procedure, and we want to set the voltage regulator for the triac circuit, the regulating. Now, just want to mention a few things here. The last hour of video where I was fumbling my way through this, I know I'm going to get comments. Oh, this video's too long. Oh, you're taking too much time. Oh, you're whatever. I don't really care. I think it's good information for people that are working on one of these amplifiers. I'm working blind on this. I've never seen one of these before, and I've never opened one of these up and worked on it. So this is all learning for me, and hopefully I can post up the video of me fumbling through this, and it'll be learning for somebody else too, because maybe they'll realize the mistakes I made or the hurdles I had to overcome. Maybe they'll have the same problems and they'll know right away what's going on, and hopefully it helps somebody. But you know, if your contribution to the channel is just posting a comment, oh, your video is too long, then maybe this video is not for you. This video is for helping people, not for your entertainment purposes. So now what I want to do is I want to power this up. We're going to see if the amplifier passes a signal, because that's the most important part of an amplifier, to amplify. So I got my load connected, I got the scope connected, and you should be able to see the scope up on the screen. We're going to turn this thing back on. Where's the power switch here? Make sure that's on. And we're going to turn on my isolation transformer and variac. I'm going to turn it down, turn that on. So we're all live and ready to go. I got a signal being fed in. This is a 2 kilohertz signal going in to one of the channels. I think it's the right channel. Make sure our switches are out. Okay. And we're going to see what shows up on the scope. It should be top trace is left channel. Let's power this thing up. And we'll see what we can do with it. So here we go. I'm going to go up to, I think up to 100 volts or so. Okay. So our triac's triggering. It's drawing 13 watts power. And let's turn up. Oh, look at that. Here's our signal. It's coming through. I'm triggering on the left. Why is it hooked up backwards? Left. That should be left. Oh, I'm feeding a signal on the right. Let me check. Let me change this. There we go. So there's our output. Now it says we should have an output with a crossover notch. And I see a crossover notch already. You can see it here, 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 here. So our bias is not set up. But we are passing signal through both channels. And I can confirm that by switching connectors and turning up the... Let's see here. As I turn it up, the wattage increases, because we're on an 8 ohm load. So everything's working. Amp's working. Great. Fantastic. Perfect. Alright, so we need to set up the regulation circuit here. So I can bring the variac up to 120 volts and check if 120 volts. Okay, let's do that. 120. We're at 120 now. We got our signal going through, and we should have a signal light on the front. I can't see because cameras are in the way. Let me turn this around. And our signal lamp is lit. Protect and clip lamps are out. Our power lamp is lit. It's barely visible. Okay. Everything's working normally. I'm so pleased about this. Just happy, happy, happy. Okay. Now we're going to set up the... okay. So we have to disconnect the input. We'll do that. Turn this down. Turn this down. Here's our voltmeter. Now we need to set up the regulation for the power supply. And they want us to disconnect the input, set top rail to plus minus 95 volts DC cold, 97 volts DC warm. And then after a couple minutes warm up, we have to adjust the idle current. And we'll get to that in a second. Let's just check this. What do we have for voltage? We're at 81 volts. So let's adjust this and see if this will bring it up to 95. There we go, 95 volts there. That is the negative supply, and here's the positive supply. 95, great. No signal, we're at 18 watts idle, which is very good for an amplifier this sized. Now we need to set up the RP100 for 2.5 millivolts DC across R133. RP200 2.5 millivolts DC across R233. I have to find these two resistors. I think they're just emitter resistors, but I'm going to have to check and make sure I know where they are on the board, so I'll be back in a minute. Alright, so I thought R133 is right here. It's an emitter resistor, and R233 is right here. Now we're measuring across one resistor, not both. So 2.5 millivolts across one of these. Now it's kind of tricky getting in here with my fingers because there's mains voltage, there's a mains voltage switch here, there's a rectifier with 100 volts 200 volts DC on it. I'm going to power this thing down and connect my probes, and then we'll power back up, and then we'll check our bias setting. Okay, so I had troubles getting these clips on the resistors on the other side. There's just no room to get your hand in there to get a clip. If I had extra long ones, I could do it. It's pretty tight. So what I did is I just tacked on some wires to the back side of the board here with where the emitter resistors are, and I just connect my clips there. It's a lot simpler, just a little extra work. So we're going to power this thing up again, and we're going to set this. Okay, I still set my variac still set for line voltage. Let's turn it on. And everything's powering up. You can see over here it's powering up. It's doing good. Let's set this one to 2.5 millivolts And I'll just have to reach around the back here with my hand. And let's turn this one up to 2.5. Okay, there's a go. This is millivolts. Okay, so we're at a quarter. Can you see that? Are you having troubles? If I shut the light off, is that better? Okay, let's slowly crank this one up. 2.5 millivolts. Wow, there it is. 2.4. And our power consumption jumped to about 20 watts, 21 watts. Okay. Now I don't know, this is probably going to change as it warms up. Let me turn it down a bit. I'll put it on the low end and I'll let it warm up. 2.5. It's an odd. 2.2, 2.1. Let's leave it there for now. Let's try the other channel. Let's turn this one up. Just turning it with my hand. Okay, right about there, 2.3. We're idling at 23 watts. 23.5 watts. Just let this, just gonna let this sit for a while, and we'll tweak these so that they're bang on 2.4, 2.5. Yeah, the spec is for setting the bias after 2 minutes of warm up. So it's been on for a few minutes now. This is gonna shut off. Turn this back on. Let's turn it down a little bit because it is climbing up. So I'll turn this one down a little bit just to get it under 2.5. Wrong way. And we'll set the other channel as well, and then we'll leave it at that. 2.4 is good. And this thing is ready to do the beans, I think. 2.3, that's still good. Okay, I'll remove these wires and then we'll put the bottom cover on. We're done with this. Okay, now that we know we got a working power amplifier, I'm going to have to go through and do all the rest of these checks. There's quite a few of them. Check full power, check DC offset, check high frequency trip point, overcurrent. I have to go through and do all these checks. There's a whole bunch of them, and I'll do that off camera. I don't need to bore you to death with all that. But one thing I do want to do right now is we'll do a full power test. We'll see if it's going to deliver 350 watts a channel, and we'll do that for a short period of time. We're not going to cook my load for 10 minutes because then I won't have a load anymore. But let me get I have to rig up inputs for both channels. I only have the input for one right now, so give me a sec. I'll be right back and we'll do that. Looking at these quarter-inch phono jacks for the inputs. XLR inputs, that's your balanced, but this is supposed to be unbalanced. It's got TRS inputs, that's tip, ring, and sleeve. Now I'm thinking just pull these out and put regular RCA phono or RCA connectors there, and that will make it a lot more user friendly. Let me know what you think about that in the comments about this tip, ring, and sleeve input. Eliminate that and convert it, or just leave it alone and get an adapter that plugs in. But for right now, I think I'm just going to, since I don't have a lot of these quarter-inch phono jacks or plugs, I'm just going to connect a signal right to these 2 points. This is the hot for the input, I believe, and I'll just tack my wires there and then feed it a signal, and then Bob's your uncle. Okay, I'm all wired in to do a power test, and I'm going to plug this in. This is shut off, isn't it? It is. And let's get this set up. Let's do this. Okay, we're all ready to do power test. I'm all plugged in and ready to go. I got it turned off and I'm drawing 0.2 of a watt. I don't know what that's going on there, but it might be something that's drawing some parasitic power. So I think I get everything set up. I got my load with a fan because this thing's going to get hot. Let's turn this thing on. A little buzzy and it settles down around 20 watts. And our amplifier should be live. Let's see. We have a protect light is not on, so we're good. So let's see if we can turn this. Now I'm going to feed it with my signal generator. I'm going to use the attenuator on the signal generator to feed it AC voltage. And then we're going to give our signal. So here we go. Start going up. You should be able to see it on the scope. Where are we at now? 12.3 volts RMS in the output. So we need to turn these down because they are going to go high. Alright. Consuming 100 watts so far. Let's keep going. What is going on here? That took quite a jump. $400 watts. Let's keep going. $36 volts on the output. 40 volts on the output. Yeah, I guess it is taking the power out to the back. Kind of scary turning this thing up. We're still at 338 watts. 26 volts output. What is that at 26 volts? That's over 100 watts, isn't it? 26.3 squared divided by 8. 86 watts. Okay, let's just see if we can take this thing up. It's 50 volts. $312 watts. Yeah, I'll turn some fan on here because this is getting hot. And this is getting hot too. Okay. That thing's cool. I think it's doing the business for sure. What we need to do now is address the cooling of this thing because this heat sink's getting quite warm. So let's do that next. Yes, this thing does go up to 350 watts. What is 350 watts? 52.9 volts RMS. And it should do that without blowing a fuse. So let's try that again. 52. There's 53. We're drawing 1.14 kilowatts, and it's doing the business. Okay, I'm pleased with this. This is working up to full power. Let's get a solution here for cooling. Okay, cooling. Now, what I want to do is use a box fan like this. This is a 12 volt, almost 10 watt fan, and this will move a lot of air. I was thinking of mounting this here and then make up some ducting or something to block the air so it's all forcing to travel through the fins, right? It's gonna fit. Now the problem I'm facing is, what do I use for power? Do I install a transformer and use that power from that to power the fan, or do I tap off somewhere in the circuit here and steal power from one of these circuits for the fan? Now the fan consumes full power. It's going to consume 10 watts, and 10 watts at 12 volts, that's what, 800 milliamps or so. So that is, I'm thinking here, if I steal power from one of these circuits, probably this one here, 800 milliamps might upset the balance of the circuits. This low power, low voltage power supply supplies the op amps and the front end of this with power, and I don't want to upset that. But let's see here, if I got it plugged in, I do. Turn it on. I just want to see what I have here on these two red windings, because if I look here on this, the AC red and AC red should be our lowest voltage windings on this transformer. Ground is center tap, the black. So if I can get a voltage off of this winding, I should be able to take some power from there. So let's see what this measures. Can you read that? Yes, you can. So here we go. And I got about 14.5 volts AC. 14.5 volts AC. So if I do some math, 0.5, let's see here, let's minus 1.4 for the dial drops, times 1.414, that should give us about 18 volts, 18.5 volts to work with. Now I have a number of solutions here for power. I bought these cheap power supplies off AliExpress. These ones are three terminal regulators. I can use either one of these. These are 12 volt regulated supplies, so I could feed the AC in one side. It's bridge rectified, it's filtered. No, it's not filtered. Where's the filtering on this? Wow, there's no filtering. Okay, that one's out. Doesn't need to be filtered. This one here, AC comes in here, goes through a bridge rectifier. Looks like we got one filter cap here, goes through a 3-terminal regulator, 12 volt, and another filter cap. So this one gives us 12 volts regulated. We could use that one. And this one here is a buck regulator. It's a switching regulator. So you put input here, AC. Why is that all dirty? Put your AC in here, it goes through the bridge, bulk filter cap, and then there's a buck regulator that's adjustable. I can adjust this to any voltage I want, and there's our output. Problem with this is noise. It might create noise. That's what I'm worried about. It's got the cheap caps too. This is a good cap, but this one's not. I think I'm going to go with this solution here. So I'll tap off the transformer secondary into this, and then we'll put it into a controller. Then we'll feed our power into one of these little controller modules. These run on 12 volts, and this will control the fan according to temperature. And we can program this to come on at 40 degrees C, 35, 40, 50, 60. And they have alarms if it gets too hot. Yeah, let's use these two modules. Let's get our power and get our fan set up. So I had a little think about this last night when I was sleeping. If I tap off this red line and this red line and I run it through a bridge rectifier, I'm going to end up with 27 plus 27, 54 volts across this capacitor. These little regulators can only handle 35 volts, and then they drop down the voltage from there and they dump the rest as heat through the heat sink. This cap's only good for 35 volts. So I want to limit the input voltage to a point that doesn't exceed any of these maximums. So if I take from the red wire to the red wire, even though I measured 14 volts between the two, I don't think that's correct. I think that's an illusion through the meter. I think we're just measuring the weird waveform, and the meter's averaging down to 14 volts. But if I actually put capacitors across, a bridge rectifier and capacitors across, I'll probably get 54 volts. See what I'm talking about? So if I do this across the, you can't see it here. It's still hidden. But if I tap off of these two red wires, this is what this is, I'll probably end up blowing up this module, which I don't want. It might work on idle, but then as soon as the amp starts powering up and ramping up the power through the transformer, this thing will just smoke. That's when I need it the most, when the fan is going to kick on. So I think I'm going to take power from one red wire, and the other I'll reference from ground or chassis, and that'll give me the correct amount of voltage I need for this module. So let me make those changes. I got the holes drilled. I'm going to mount this module here, and I'll mount the other module beside it. And I got the fan already mounted, and that's in place, secure. And it's just a matter of wiring it up and testing it. Alright, here's my solution for cooling. Fan is installed. It's mounted down to the PCB board, secured with adhesive. That's where it's going to sit. Now, I got both boards here mounted on the side plate. This one here, I got it drilled and mounted here, but I haven't mounted it. I got a connector here between the 12 volt supply and the fan controller, just so if I need to disconnect it for whatever reason, I can do that. The temperature sensor, this wire here, you can't see it. I don't know if I turn this around. I mounted, I'll just do this. I mounted the temperature sensor over on this side because the output transistors are on this side, and that's where I figure most of the heat's going to be generated. So I put the sensor there, and I want to run the wires back to the module, and everything seems to be in order. I got my little piezo alarm here. If need be, it can beep. But first thing I want to do is I want to check. I tapped off one of the red wires to ground, and I just want to see how much voltage I have on my little 12 volt power supply. So this is plugged in and it's ready to go live. Let me get my meter. Turn on the amplifier. You hear the fan ramp up and then settle down. Fan's on low right now. If you can hear it, it's pretty quiet. And that beep on power up, that's to let you know everything's working good. So here's our supply for the 12 volt regulator. What do I have here? I got almost 26 volts. That's good. So we're not exceeding anything. This thing's barely warm. Okay. So as part of the cooling management of this amplifier, I took this little piece of insulating sheet, just cut it up quick to fit it, just to fit. And what I'm doing is I'm going to make a ducting for this so that it kind of helps the airflow go through the heatsink instead of escaping around it. So I'm just going to put that in place. I'll fine tune this and cut it to shape what I need, and probably tack it down maybe with some blobs of silicone or something, and just so that, you know, like the air doesn't get lost. So I'll put this, it'll help. And another thing I'm going to do is on the lid, I'm going to be putting these foam strips right here and right here, and that'll coincide with the two outer fins, and that'll help block the air from escaping underneath the lid. This will help seal it. Purpose is to get all the air from this fan through to the other side to help with the cooling. This fan, when it's powered on, it runs on low temperature, so this heatsink will always see air flowing over it, and I doubt it'll ever get to the point, well, when we start pushing the amplifier, of course it's going to get hot, and this is going to start kicking in and providing some airflow. This fan will move a lot of air. We'll try it out after I'm finished making these fine tunes here. So let's see, this here, this lid goes here. So yeah, all the hot air escapes here, all the cold air comes in from this side. That's the plan. Okay, we're ready to do a test of the fan cooling system. I got it all connected to my load, got an input signal. We're going to ramp it up, start with 100 watts per channel first. Let's turn this thing on. And let's turn up the power. I got I got my voltmeter here connected, so I'm going to use to monitor the output. And first I'm looking for 20 volts RMS, so let's turn this thing up. Where are we at? We're at 8 volts. 10. Okay, that's 20 volts on the meter, 100 watts RMS per channel. We'll let this thing cook for a while. It's barely working. Nothing's even warming up. The heat sink's still cold. Let's turn it up to 200 watts channel, and that should be 40 volts RMS. Yeah, it's 40 volts, 200 watts per channel. Now we're getting a little heat. $850 watts going in, 400 watts going out. So you can safely assume that there's probably 450 watts being radiated by this. So very noisy transformer on this. Okay, the fan's ramping up. Can you hear the fan coming up? Yeah, it's working like the charm. If we had the lid on, this would be cooling a lot better. Yeah, I think it's successful. We're still at 200 watts a channel. Okay, I'm just going to shut it down. Shut down the signal. Let this thing cool. We're running about 55, 60 degrees on this side. This side's a lot cooler, 45, 42. Yeah, this side's quite a bit warmer because the air is kind of escaping here. It's just coming out and going up, and there's really no airflow back here. So once you put the lid on, that'll fix all that. And then it ramps down when it cools. I'm pleased with this result. All right, let's wrap this up. Those fan controllers are a wonderful thing. You can put them in almost anything you want as long as you have a 12-volt supply and, you know, a fan. I really love these things. They're a savior. And you can just install this in any amplifier. If you have an amplifier that runs hot, you want to keep it cooler, put one of these in. And you know, when it's running low, you don't even hear it. You can barely hear it now. It's slowed down. It's still dropping. And yeah, excellent. That was a success, I think. Well, there it is. It's complete. It's done. I'm quite pleased with how it turned out. I wasn't quite pleased with how it came, the condition it came in. It was pretty much baked inside and burned out. And I can see why the previous tech gave up on it. It was just too much work for you know, an hourly tech to just dive in and try and fix it. It would be impossible to make this thing profitable repair. Now, when I put the poll up on YouTube on the comment section, I had the 3 amplifiers, and I waited a day or two, and then I came up to the poll and looked at it, and the Carver was up ahead of everybody else. So that's why I grabbed this and started working on it. And then a day later, the Onkyo pulled ahead and beat the race. So yeah, I'm sorry I didn't put the Onkyo first, but it's coming up. I still have work to do. I have some bills to pay here. I got some cleaning up to do. Things are piling up, and I have to get rid of some of the work that I've got waiting for me. I'm in the middle of a realistic STA 2500, and I'm waiting on parts for that. I'm kind of concerned because I ordered the parts quite a while ago and they haven't come yet. So waiting for that. So if the parts come this week, you might see that next week. The 2500. It's a nice receiver from Realistic. And then I have the Sansui 9090, the non-DB version. So that's waiting. It's been sitting here for, I think, over 2 months now. The owner's probably getting ready to call the police on me. But that is coming up as well. So I'm going to start on the Sansui as soon as this is done. And that's the Realistic is done. And then we'll keep going, keep plugging away. So this is, oh, it's a little dirty. This is a nice professional amplifier. It's not meant for home use, as you can tell by the inputs, but it could be converted for home use. I don't know why you'd want 350 watts of channel in your home, but you know, to each your own. This is quite a beast though, and I learned a lot working on this. I've never worked on a Carver before, and this is my first one. So yeah, a lot of learning going on with how the power supplies work, and it's quite interesting, to tell you the truth, how it was designed and how it's put together. And it's got a bit of a professional quality build feel to it because it's got industrial parts, and you know, it's got the fiberglass board and all that. But yeah, this is a good one. So thanks for watching, and we'll see you on the next one. Take care.